Just like all K values, with KSP, we can do calculations. We could solve for K, or we can use K to solve for the amount of chemical in our equilibrium. So when we're trying to find out how much something dissolves, it takes very careful lab measurements. So it could be related to how much solid we've put in. Because they're dissolving in such small amounts, it's usually a little bit trickier than that. But luckily, we normally have a numeric value. So first and foremost, just like K can be greater than or less than 1, meaning we favor products or reactants, when KSP is greater than 1, we could kind of say it favors the products or it does dissolve. That's when we say it is soluble. A lot of the solid has turned into ions, enough so that we say that it is favored. The smaller the KSP, the fewer the ions there are. But as I referred to earlier, if we're comparing KSPs to one another, it's super important that we also pay attention to subscripts and coefficients, because the math, as we're about to see, gets a little bit different. And when we are doing these calculations, it's the same idea as before. We have a reaction. The reaction is a solid breaking into ions. We've got that right there. We have initial amounts. Most of the time, we think about those initial amounts as being 0. We put in a solid into pure water, no initial amounts. The change is based upon our subscripts, which become our coefficients. How much of that ion are we making? Based on the charges of our cations and anions, the subscripts on those, that determines how much, +1, +2, +3, etc. The equilibrium will, if we started with the 1, that equilibrium row would always be equal to x, or maybe 2x or 3x. So the x in this case is how much have we made, or with solubility, since it's always the same sort of problem, the x is what we call molar solubility. Sometimes it'll ask, what is the solubility of it? Sometimes it'll ask for the molar solubility. Sometimes it'll say how many moles of solid per liter can actually dissolve, or what is the molarity of a certain ion. In any of those things, we're kind of looking for the same thing. We're using our K expression to find X. It could ask specifically for the concentration of one ion versus another. In that case, make sure you're paying attention to the numbers. But very often, the general solubility is we're just solving for X. So when we do that, we need to look at our initial solid. When it's a 1-to-1 ratio, whether they're both +1 and -1, +2, -2, whatever that is, the math comes out really easy. It's one of these for every one of those, or KSP is equal to x squared. But once we start to have concentration or subscripts based upon different charges, yes, it's still just the concentration of A in there. But when we set up our Rice table, we would see that we make 2 A's for every B. So we have a 2x, that 2x gets squared, not just the x, but the 2 as well. So then this comes out to a 4x cubed. If we had a 3-to-1 ratio, we would see as well the 3 gets cubed and multiplied. So we don't want to look at or try to memorize all of these. Trying to memorize every possible scenario for every possible equation on the AP test, we know is going to be a disaster. So thinking about your subscripts, recognizing that subscripts turn into coefficients, subscripts turn into exponents in K expressions, but they are also involved in our change row in terms of the coefficient and the stoichiometry of how much of that ion we make. So that's where a Rice table, even though solubility can be a simpler process, still comes in really handy, helping us to make sure we don't make silly mistakes like that.